Okay, heat of reaction from standard enthalpies of formation. So we can calculate or estimate delta H by using other equations and adding them together like that. Or we can use a table of standard enthalpies of formation. So delta H is the change in enthalpy. We can define 0 as something that's convenient for us. That's what we've done with altitude. We measure altitude relative to sea level. Is that absolute 0? No, it's a convenient 0. Absolute 0, I suppose, would be the center of the Earth. That's going to be a little difficult to measure, right? It doesn't matter when we're just measuring changes. So what we've chosen to do is to measure enthalpy relative to the enthalpies of pure elements in their standard states. So we're saying, okay, whatever this element as an element would be, we're going to call that 0, and then we're going to see what changes relative to that. So what are the standard states? These are specifically defined. So for a gas, the standard state is that pure gas at 1 atmosphere of pressure. If it's a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest. Usually that's 25 degrees Celsius, which is approximately room temperature. If you have something in solution, then it's a concentration with exactly 1 mole per liter. And those are the standard states for the elements. So standard enthalpy change, we had delta H, and now we've added this degree symbol, this little 0. That indicates standard states. So this is standard enthalpy change. Standard enthalpy of formation, so we've got standard enthalpy change, and now we put an F here indicating formation. That's the enthalpy change for making 1 mole of a pure compound from its elements. The elements have to be in their standard states. The standard state for these pure elements gives us a delta H of formation for them of 0, because we said that was going to be 0. So how do you know what all these delta H heats of formation are? You look them up in a table. This is table 6.5 from the chapter in your book. There's another much larger table in the appendix, and you might need to use that. If we look at this, let's just start at the top here. Here's bromine, Br, in the gas state. Well, that's not the normal state for bromine. It's not the standard state. To make Br gas is 111.9 kilojoules of energy per mole. That's positive. You're going to have to put that much energy into bromine at its standard state to make it into bromine atoms in the gas state. Bromine would prefer to be Br2, a liquid. That's its normal standard state. And so the heat of formation for that is 0, because that's baseline. A lot of the standard states you can kind of predict by just looking at the periodic table, but you can also just look at the table, and anything that has an enthalpy of formation of 0, you know that that's the standard state. Carbon can be in the form of graphite or in the form of diamond, and graphite is the standard state. For elements like the diatomic elements, the horses need oats for clear brown eyes, those guys, their standard state is going to be a diatomic molecule. And whether it's a gas, liquid, or solid, you can figure out by looking at the color on the periodic table. So if it's red, it's a gas, blue, it's a liquid, black, it's a solid at 25 degrees Celsius. Most of the other elements, it's just going to be monatomic elements, whatever state they happen to be. So standard enthalpy of formation, also called standard heat of formation, just like we called the enthalpy of reaction, the heat of reaction. So the heats of reaction for elements are 0. It's like being at sea level, and we measure everything relative to that. So you can go above sea level or you can go below sea level. If you're going below, then your heat of formation, standard heat of formation, is negative. It's like a negative elevation change. So let's look at how this works. So if you're making methane from the elements, what you're going to do is you're going to write this equation so that you have the elements. We're doing methane, CH4, and so we need carbon and we need hydrogen. And we want these elements to be in their standard states. So you can look them up in the table. They are the ones that are 0. So solid carbon as graphite is 0, and H2 gas is 0. So the heats of formation for those things are 0. So the standard heat of formation for methane is minus 74.6 kilojoules per mole. People have done the experiment, measured it, tabulated results, etc. You look that up in the table. So under carbon, here's methane. Standard heat of formation for methane, minus 74.6 kilojoules per mole. Whoops. That's not at all what I wanted. I'm lost. So this is what's called a formation reaction. Whatever we're interested in, we're forming it from its elements in their standard states, and we're going to make 1 mole of product. When you balance the equation, you may end up with another number. You may end up with 2 or 5 or something. You need to divide then to get 1 mole as the product. And so you can end up with fractions in your coefficients. And here that's necessary. So let's look at carbon monoxide. So carbon monoxide is composed of carbon and oxygen. So those are the 2 elements, carbon and oxygen, but we have to figure out what the standard states are. So we look at the table and we figure out which ones are 0. So for carbon, it's the solid graphite is 0. For oxygen, it's O2 in the gas state is 0. Okay, so we found out what the standard states are for these. Now, is this equation balanced? No. So if we're balancing this, what would we do? We say, well, we've got 2 oxygens here. I'm going to have to put a 2 over here to make 2 oxygens over there. And then I'm going to have to put a 2 here. Now it's balanced. But to look at the formation reaction, I want to know how much to make 1 mole of this. How do I change a 2 into a 1? Divide by 2, right? So I'm going to divide this side by 2, and I have to divide everything over here by 2. This was an understood 1, and I divide by 2. And so I get solid carbon as graphite plus half of an oxygen molecule. Well, it is what it is, and that'll give me 1 carbon monoxide. The 1/2 fractional stuff doesn't work very well if you're talking about molecules. It works perfectly fine if you're talking about moles. So I need 1 mole of this and half a mole of oxygen to make 1 mole of this. It has to be 1 mole of the product. Okay, so there's the reaction. That's the the formation reaction. And then to find the standard heat of formation, we look it up in the table. So write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Well, we're trying to make sodium chloride. What are the elements? Sodium and chlorine, right? So we'll write Na, and we'll write Cl, we got plus in there. We need their standard states. So we can think about it, or we can go to the table and look. Oh, this is the table for the other things that aren't in this first table. So here in the table under sodium, solid, that's the 0. For chlorine, it's Cl2 gas. So that's the formula I need to put in my equation. So the sodium is NaS, and chlorine is Cl2 in a gas state. That's how I get the formulas for those. I need to balance this reaction, but I need to end up with this coefficient being 1. You can do it like we did it for the carbon monoxide one. Balance it, regular, and then divide to get the right coefficients. Or you can use fractions to start with. I need 1 sodium chloride, 1 mole of this. So that means I need 1 mole of sodium, and I need 1 mole of chlorine, but this is actually 2 moles because it's Cl2. So I need 1/2 of that. And then I go look up the standard heat of formation for that. So I go to my table, and here's sodium chloride solid, minus 411.2. Minus 411.2 kilojoules. Kilojoules per mole. My product is always 1 mole. Any questions? Let's do the second one. Lead nitrate. So I've got, let's give ourselves a little more room than that. Pb, NO3, 2. Right, solid. We are not writing the equation for how you might form these. We're not splitting things into ions or anything. We're just looking at the elements. So this one has 3 elements, right? Lead and nitrogen and oxygen. So I need lead and nitrogen and oxygen. Well, we can guess what the standard state for nitrogen is. It's a diatomic element, and it's a gas at room temperature. And same thing for oxygen, but you can also go and look those up. Lead. Well, we could guess that lead would be a solid, but it's a good idea to go look it up. And this is why I pulled in this other table, because lead isn't in the first table. But here's a section from Appendix B in your textbook, and here's PBS, right? So there's the standard state. This table has 3 different columns. We haven't talked about delta G and S yet. We'll talk about those later. We're just looking at the column that's delta H. So I got my standard states, and then I need to balance the equation. So I have 1 PB and I have 1 PB. So that's okay. Here I've got N2, and how many nitrogens do I have over here? 2 nitrogens. Well, that's convenient. I have N2, and over here I've got 2 NO3s, and each of them has 1. So there's 2 Ns. How many oxygens total over here? 6. So what do I need to do to this O2? Multiply by 3. Come on. So this is a 3, and a plus in there, and a plus in there. So that's balanced, and it ends up with 1 mole of product. And I'm supposed to write the heat of formation. So I have to go to that table again, and I have to find lead nitrate. So here's lead nitrate, solid, minus 451.9. Minus 451.9 kilojoules. Any questions? So how can we use this to calculate heats of reaction? Standard heat of formation is the formation of a compound from the elements. If we reverse this and take the compound and decompose it into its elements, the heat change is the same, the sign is different. So what we do is we look at the chemical equation we're trying to write a heat of reaction for, and we say, well, what's going to happen if we decompose the reactants into their elements and then use those elements to make the products? We can look up the heat of formation for the different compounds and just add them together. We can write any reaction as a sum of the formation reactions. That's using Hess's law. That gets a little tedious. We can also just say, well, the heat of reaction, the standard heat of reaction, is going to be the heats of formation for the products. If they've got a coefficient, you have to multiply it by the coefficient. So that's going to be forward direction. And then we're going to take the heats of formation of the reactants, and we're subtracting here because we're saying we change the sign when we take those things apart. This capital sigma just means the sum. So the sum of that for each product minus the sum of this for each reactant. And n is just representing the coefficients that are in the reactions. So here we're looking at methane burning again. So what we're going to do is we're going to take, let's see, where are we starting? We're starting right here. We're going to take our reactants apart into the individual elements. This isn't happening in real life. We're just mentally doing this. So I'm going to take CH4 and separate it into its elements, carbon and hydrogen. Oxygen is already in its elemental standard state, right? So now I have all of the elements. I know the amount of energy that would be released when I form methane. If I take methane apart, it's going to absorb the same amount of energy. So decomposing the methane is plus 74.6. Now I'm going to take these elements and I'm going to put the carbon and the oxygens together and form CO2. I can look that up in the table. The heat of formation for 1 mole of CO2 is minus 393.5. So when I make 1 mole of CO2, I release 393.5 kilojoules of energy. Then I can take the hydrogen and the oxygen, the other oxygen, and make water. Well, the heat of formation for 1 mole of water is minus 241.8. If I'm making 2 moles of water, it's twice that. So I've got this being released and this being released. This change here is the sum of these individual pieces. But we don't actually have to write out all the equations and do them all up. We can just do the sum of the products minus the sum of the reactants. So the standard heat of formation, the standard heat of reaction for this is going to equal the heats of formation for the products. So CO2, so here we've got CO2. So that's negative 393.5. And we've got 2 waters, so plus 2 times how much is changing when we make a mole of water. And we're going to take that and we're going to subtract the heats of formation for the reactants. Well, the heat of formation for O2 gas is 0 because it's already an element. So the only one we have to worry about is the one for methane. So we're subtracting negative 74.6. So that's the sum of, well, let's do it this way, plus 0. So heats of formation. So we got minus 393.5 plus 2 times negative 241.8 equals, and then I'm going to subtract negative 74.6. Be careful with your signs. Well, I did something wrong. I'm arguing with my calculator. Minus negative equals, I'm getting minus 802. 0.5 kilojoules. Any questions? Okay. There are two more examples here for practice 6.11 and for practice 6.12. I wish I had time to do those in class with you. What I'm going to do is I'm going to post YouTube videos from last spring where I work these out. So those are on the playlist. You need to go watch them, okay? And then ask me questions. This next part, 6.10, this is a great section, but I'm not testing you on it, and we're out of time, and so I'm not going to lecture on this either. You can read this. It's good for general knowledge. It talks about energy use in the environment, but I'm not going to test you on that. So, and there's an example there, but it talks about renewable energy, blah, blah, blah.